Hey everyone, welcome to online chemistry. Hey. So I'm going to try to make this as interactive as possible, and I'm going to try to be filling in the blanks. The idea is that if you print this off, or if you have it on your computer or something, so that you can get to it, you won't have to write everything down that I say. It's like all mostly said, and you can just fill in things as you go along. You'll notice that I've done these things where I've embedded links in here that are in relevant sections. And I did that throughout. And the idea is that if something I say doesn't make sense, or you want someone else saying it a different way, that really can make a big difference. So just keep that in mind. I'm going to show you guys some of the links as we move through this. Okay, so first of all, this chapter, chapter 5, is probably one of the more theoretical chapters where you're really having to do a lot of understanding what's going on with the atom, but we aren't covering the whole chapter. And in fact, we have a summary page. So I want to show you guys at the end, if you go to page 8, is that last notes. I passed this out, or a page that looks like this, last time. And you'll notice that I've got all these pictures on here, kind of some helpful hints for everything. This is basically like a great summary page. And now that you have open notes, you are super duper lucky. I want to point out something. There's these letters here, these SP kind of letters right here. See those? They're like huge in this chapter. But the great thing about it is that if you know the bonding going on, so if you know that it's linear, you can already go ahead and say that that's SP. And if you know something's trigonal planar, you can say, oh, that's SP2. If you know it's tetrahedral, you can say, oh, that's SP3. If you know it's trigonal bipyramidal, that's SP3D. And if it's octahedral, it's SP3D2. That applies for all of these other guys in this category. They all end up with that same set of numbers, and those numbers are called hybridization. And it's something that you get asked a lot of questions about. So they'll say, oh, we have this molecule right here. Can you tell me what's its hybridization? And you just say, oh, it's SP. See how there's an easy kind of a shortcut to this? There's two more things to note, is that in this category, and we'll mention this one, kind of like the max that you can have is SP3. This is what a lot of things are. That's that tetrahedral situation. But in this category, you see how this is SP and how it's like it's missing two P's? So this one has two non-bonding P orbitals. So just keep that handy. That information is going to come into play when we talk about double bonds. This one has one non-bonding P orbital. And what you want to know about this is that those P's and those P orbitals can do their own special kind of P overlap. And these are the orbitals that are going to be able to make the double bond part of a double bond or a triple. This page is your resource, huge resource for everything you need. All right, so I'm going to go back to that first page. We're going to talk about bonds. You might say, why do we care? Well, chemistry is all about breaking bonds and making bonds. It's what your body does all day long. So that's why we care, because we're trying to break and make bonds. So we have this thing called valence bond theory. And this is one of those things where you have a theory and then they kind of keep upgrading it as the years go by. But valence bond theory, it describes a covalent bond as something of half-filled atomic orbitals. And the key word here is overlap. I've got a picture to show y'all in a second. Of half-filled atomic orbitals, each containing 2 electrons. Now you already knew that they contain 2 electrons. If I point at this bond, how many electrons are there? You would say 2. How many are there here? You would say 2, so you know that. The only thing we're talking about is we're just saying that before we just said draw a line, it represents 2 electrons, and that's the covalent bond. Well, now we're saying, hey, do you guys remember that really there's this 3-dimensional space that electron went into, and it was like a sigma space? Do you guys remember that? That's what we're kind of saying. Well, if you got an electron in one space, so it would be like on the hydrogen right here. So see, there's hydrogen's electron. And then if you have like another electron in like some other 3D space, so like we're just gonna make it like here. And I need to do this for a hydrogen-hydrogen bond, so I'm gonna move him off of that atom for a second. So like if this is a hydrogen, what we're saying is instead of just drawing a line between the two hydrogens and saying, oh, hey, look, these are a bonding pair, is what we say is like this guy kind of gets close and then this guy kind of gets close. And that is overlap. See, because they are thus overlapped. So not a tricky thing. It just seems weird at first. You're like, overlap, half-filled atomic orbital. Well, when there's one electron in it, that's a half-filled atomic orbital. Because you can only have two in the bond, and one is half-filled, and two is your max you can do on any orbital. S, P, D, or F, you can only have two. All right, so those are your half-filled atomic orbitals, each containing 2 electrons. And they yield a pair of electrons shared. Hey, this is covalent chemistry, so we're shared between the 2 bonded atoms. So when they make this kind of a shape, they kind of then can jump in and out of each other's space. So like that one can go there and they can move all over. Y'all good? Hopefully you're good. So there are 2 kinds of bonds. There is a sigma. I know you thought I was about to say single, didn't you? And a pi. Now, I don't know why we changed the names on these per se, but look. So your sigma bonds, that's your single bond. And they both even start with S's. Now your pi bond, it builds more bonds onto your sigma. So like what we're saying is that the pi bonds are double or triples. But it's the double and the triple part of it. I'll show you what I mean. So let's say we're talking about sigmas. I'm going to make sigma's color be red-ish. So here's our sigma color. So like this is sigma, this is sigma, this is sigma, this is sigma, and this one looks like it's between. So I'm going to call that one sigma. So this one has 5 sigma bonds. That didn't look very much like a sigma. And then over here, so 1, 2, 3, 4, 5, 6. That's 6 sigma bonds. So now you're like, but that other thing was a double bond, and you said something about double bonds. Yes, yes, yes. So this guy right here, that is the second part of this bond. You gotta have the thing I've colored kind of reddish pinkish. You've gotta have that in place first. They call it frameworking, or you gotta have that first, and then you can get the double bond. You can't just jump to a double bond. You gotta have that in place. So this one has 1 pi. And then over here, this is 1 and this is 1. So I need to have 2 pi. So when you get structures like this is a really common question. It'll say how many sigma bonds and how many pi bonds. So you count all of the singles just like we did in both those cases, so it's not tricky. And then you go back and you count only the doubled part, like the additional line, as 1 pi bond per section. And like this next line is a pi and this next line is a pi. And of course, we'll show you exactly what they look like, which is kind of crazy looking. Then we have hugely important concepts. Chemistry is all about asking about bond strength and bond length. All right, so bond length. Single bonds are longer. Remember, we got that little sigma. Double bonds are not as long as singles. Remember, just what we were just saying, sigma. So that was that color right here. That's your sigma. That's your sigma. That's your sigma. That's your sigma. Your double bonds are about medium, and the triple bonds are really tight, and they're really narrow bonds. Now notice that for strength. So here's your strength. Watch what happens with your little arrows. Do you see how it's reversed? So if we were looking at these molecules, this would be the longer, this would be a long bond, and this would be kind of like a medium length bond taken together. That's medium together, and that's long, like if I'm comparing those two. But then if I was asking about strength, I would say this one is weaker and this one is stronger. And yes, the more bonds, the even stronger they are. So of both of these molecules, this is going to be your strongest and your shortest bond. So if you can get all those principles I just said, you've got the majority of the chapter nailed down, in all honesty. If you've got those two, you're okay. Then this is a reminder about your atomic shapes. We talked about this in chapter 3. I doubt that you've forgotten it. Right here, this S shape, remember that that's like a spherical shape? It looked kind of like that. I should have used the highlighter on it. It's like a spherical shape. And then if we were talking about the P's are kind of like this kind of a shape. Do you remember that? If you don't, go back and check. Or you can just Google S orbitals, P orbitals, you'll get those shapes. Okay. This is what is important about bonding. We've mentioned this before too in a different way. So, a certain unique distance between two atoms allows for the lowest energy bonding. Now at the very top here, I didn't click on this link, but if you click on this link, this is only like 8 minutes long, and she goes into everything you need to know about the whole chapter. Like this whole chapter only gets one video. And if you click on this link, I did already pull this one up. The guy's voice is kind of boring, so I'm just going to scroll to the part that's important. Okay.
Let's use this graph of potential energy versus the distance between the nuclei to see the energy as zero as they move closer together.
Okay, so look.
As they move closer together.
Pause him. So this is what we're saying. So this over here on the right-hand side, you see the 300. I can't write on this screen because it's YouTube, but on the right-hand side, it says 300. So that's a bigger distance than the left-hand side. That 0 is like basically the atoms being on top of each other. And so if you look up at the top so far, if something's at like 150, do you see those atoms are pretty far apart? Those atoms are not bonding. They are too far apart. They don't see each other. They can't interact with each other. Now if I jump it on forward to like, okay, here's some more. So look, in this case, and you can watch it yourself. So you can see as the atoms start to get closer together, like, so go leftish and down this spacing. So as they get closer together, do you see how there's that bottom point right now? And you can see the bottom of that little curve. That is how it looks when you have two s orbitals really well overlapped. And the things all to the right are not good. I can't remember. Do we do one more closer one? Yep, look. And then look, this is where they're kind of stuck on top of each other, and that's not good. Whoops. So anyways, that is what you're looking for. That's what we're talking about when we're talking about these bonds. And that was this link right here. So that's the first thing, is the distance matters. You know, like they both have nucleuses that are both positive, and if you get those nucleuses too close, they're going to repel. You want it to be just close enough so that the other atom's electrons can interact with the opposite atom's nucleus, but you don't want them to be too close. It's like a certain distance. That's why it's a certain unique distance, and of course it's unique to whichever atoms you're talking about. Then the other thing is that matters is not just the distance. So you also need the orientation to be right. And what that just means is that they have to like be bouncing into each other, like just so. You want it to allow for the greatest overlap. Greater overlap is possible when orbitals are oriented so that they overlap on an axis. I'll show you in this picture right below, between the two nuclei. So if you look right here. So this is an example of a p orbital and a p orbital overlapping, and you can see like how much more of this can be overlapped. When they're directly overlapping, that would be on an axis. So like that's your axis. They're overlapping on an axis. Whereas like these guys don't have as much that they're overlapping on. So we're going to talk just a little bit about sigma bonds. I'm trying to remember what overlap direction is. I was going to say important. I'll come back to it. It'll come to me. So the first type of bonding is sigma bonds. And remember, that's the same as being a single bond, but we use that fancy word sigma. So sigma occurs when two electrons, remember every orbital can only have two, when they're shared directly along, or actually I should say between. I was going to say along the axis of, but let's just say between two atoms. Here's the nuclear axis. Along the internuclear axis, that just means, you know, up here we had this like line. So it's an overlap along that line. And if you want to play around with stuff, this is kind of a cool sim. I had some suggestions to try 1s and 1s, 1s and 2xy at these distances. I'll do just the 1s. So this is 1s and 1s. And I'm going to set, actually I'm going to do a big distance. So these shouldn't be overlapping, right? So I'm going to calculate it. So see, look, they're not much overlapping. But then I'm going to get them close together. See, they're closer. The perfect distance is like around 70-ish. So this is, there you go. Now, watch what happens when I put them like on top of each other. So that doesn't look like a bond anymore, does it? It's like the atoms have like somehow done some weird melding or something. I don't know what it is. But that is not the look of something that's bonded. They should not be on top of each other. This is the look of something that's bonded. You can play around with it. Like I said, I had some other suggestions. Try the 1s and the 2xy. The 2xy. Actually, let me try the xy and the xy. And I'll show you all the xy and xy. So 2xy, 2p, oh, I guess I meant that, 2px and 2px. Let me put them at that distance. So look, see how they are opposites? If you don't want them to look opposites like that, just click diff. So now you can see the overlap. You see it? So see, like, these are bigger. They don't have to get as close to each other to start doing the overlap. But like, here we'll put this at like 70. So see, kind of, that's a pretty good overlap. You know, 200 would not be an overlap. See, not overlapping. And like 0 would be nothing. Nothing. Okay. Y'all know I like Sims. I think they're fun. All right, so here's the 3 ways. There are 3 ways that you can do this sigma bond. Remember, we're talking about sigma, so don't get all confused. We're talking about sigmas, which are the single bonds. Sigma bonds, sigma bonds. So notice they all have something in common. So, and I know this is confusing. That circle is not the electron. That circle is the nucleus. So I'm going to add in, so here's a nucleus. I'm sorry, here's an electron, and here's an electron. So now you can see that the electron regions are overlapping. So this would be like an H and an H. That's their little bond, and those electrons are moving back and forth. They're just moving all over the place in that whole region. Trying to get to grab it so I can move it. It's not letting me do it. But just imagine they're like, he's all over here and he's all over here. They're all over the place. Now you can also do a end-on-end overlap if you have something like H. Notice that looks the same. So here's his electron. And then if we have Cl. Now if you remember, Cl looks like this at the end. He also had an S also, but we're not talking about his S. His S is all filled up. So here, look. He's got just one. Notice, see, he's got an extra space. So he's got just one in that orbital. And so they're both flying all over the place because they're close enough that they can bond and be shared. And then the last example of a sigma bond. Remember, I'm doing that chlorine example again. So this is the very last p orbital. The other p orbitals aren't doing this. It's the very last p orbital. And you'll notice, blah, they're running all over, and this one's running all over the same place. So that shows you what those look like, and all 3 of those, again, are considered sigma bonds. They would all be drawn with just a single bond between them. Yay! And here's the Newton stuff, some Newton stuff right there. And I'm going to finish this video right here with a little thought, and I have more that I can say on this, but just a little thought. And this is the whole reason why we do hybridization. Then I'll do a next one I'm trying not to do these too long. So what we do know is we know that BEH2, BH3, and CH4 form compounds and that they have identical bonds. So I'm going to do BE. So we know for sure that this happens. We also know for sure that this happens. And we know for sure that this happens. Oops, sorry, that's an H, that's behind the screen, that's coming out from the screen. We know that happens. All right, so there's a problem with what was just going on, because what these guys are doing looks different than what was going on up in that section above here. So BE looks like this. Here's the guy in the middle, and his, if we do like his little configuration, so his 1s, they aren't involved in the bonding, but here's his 2s. So notice something. His 2s is full. If you're full, you can't overlap. Like you're full. Like look up here. Up here in this other section where we had these guys. The only ones that did the bonding were the ones that had a space. Then they can bond. Look, he's full. He can't bond. He doesn't have any room to bond. And yet science says, well, we know that this compound exists and that it does form a bond. So that's the first kind of a situation. So what's the problem with him making two identical bonds? Well, and that was supposed to be, sorry, BE H2. Yeah, so the problem is that the sigma, or that the S orbital on the BE is full. There's not room for it to be like shared. Like he can't take it. It's not like you can take hydrogens and make like a group of 3 or something. You can't do that. All right, so that's the first issue. And then the other two represent another issue. So, and they also have some of the similar issue too. So with boron, he's got his 1s, that's awesome. That doesn't do anything. Then we have our 2s, and then we have our 2p. There's one there, right? We've got the other ones that are open. So first of all, we have 3 bonds. So what this means is that boron needs a dot apiece in each of them. But what we're seeing is, look, both of them are stuck here, and then there's one that's free. So you could say, okay, well, at least I've got one that I could bond and make and do things with. That's true. You do have one. That other set is all stuck. You can't do any bonding with it as the way it looks right then. Here's the other problem, is that, we do know that there are 3 of these. And we also know that all the bonds are identical. So it's not like you can say like one is a 2p overlapping with an s, and then like these two are something else weird. There's something that's going on to make these all look alike. And then the last case, again, carbons, 1s, 2s, 2p. So, hey, he's got 2, so, he could help with that bond and that bond. But again, we have a problem. So this is the problem that we're faced with. It all worked fine up here because they all had a space. They all had one electron spot open that they could do the bond with and have it be a straight sigma bond, and it was fine. And these guys, they don't have the openings. We know the bonds are supposed to be the same, but the ones that do have the opening don't have enough to make the rest of the bonds. That's why everyone got to thinking about it and decided to think of things as hybrid atomic orbitals. And last note is that hybrid orbitals only affect the middle atom. So he's the one that's changing. The other guys, nope. Be's the one with the problem. Be's the one that's got to change. Same with boron, same with carbon. It's only the middle atom that does the hybridization. All right, so that's the beginning.